Alrighty folks, I'm going to show you the best way to perform the refraction lab. You're going to need yourself one of these laser ray boxes set to the single laser beam setting. You're also going to need one of these polar graph paper pieces, and you're also going to need one of these D-shaped semicircular pieces of plexiglass. And the best thing to do is to put this plexiglass very carefully on the graph paper, lined up so that the center of the plexiglass is along the center line. So I'm going to measure quickly the size of the face of the plexiglass. Looks like it's about 8 centimeters, so I want the 4 centimeter mark to be right there on the center of the polar graph paper, and I believe I've done it. Maybe a little shade over here, a little closer. Okay, that looks really good. And now the way this works is when you turn on the laser, you can see that when it enters the plexiglass, it refracts and bends towards the normal, and when it exits the plexiglass, it refracts and bends away from the normal. But the reason for this choice of shape is that if you hit the exact center of the plexiglass, then it does refract on the way in, but it does not refract on the way out. In other words, the normal is perpendicular to the outer edge, and so you're leaving along the normal and you don't bend away from the normal in that case. So the alignment is very critical on this. So the best bet is to leave the D-shaped plexiglass on the paper and turn the paper. So we're going to start by coming in right over the center line, 0 degrees angle of incidence, and you can see that we have 0 degrees angle of refraction as well. If you have trouble finding the laser on the page, you can use a pen or a pencil or something like that to determine where it is. And then what you're going to do is you're going to turn the paper in 5-degree increments, realigning each time that you hit the center of the D-shaped plexiglass. Now look, if you manage to get to 6 degrees and you want to go ahead and use that, that would be fine. You just write down 6 degrees. But I think with enough finagling here, and that's an actual word, we can get this to work out. And you can see that I'm coming in, well, it's somewhere between the 5 and the 6. There we go, right over the 5. And then I'm leaving over the 4 in this case. So I would write down angle of incidence 5, angle of refraction 4. And we keep going for many different angles. Again, each time making sure that we're striking the center of the D-shaped plexiglass. This gets really difficult when you get out here to like 75, 80. Really difficult to work on, so take your time, be patient. These data points are important because this angle here will always be bigger than this angle here, and if you want a good spread of the angle of refraction, you need to go almost all the way to 90. Now 90 of course will not work. I'm sorry, that's only 45. 90 here will not work because you're not really going to even enter the plexiglass. So probably 85 is going to be your biggest angle and also your biggest challenge. You may notice that there is a bit of a reflected ray that skates off the flat surface of the D-shaped plexiglass. We ignore that one. We're not doing a reflection lab. We're doing a refraction lab. So we want to be finding this one over here. Once you take your data of all your different angles of incidence and angles of refraction, then you need to go into the data table and find the sign of each of those things. And the reason for that is that this is a lab having to do with Snell's law. And so Snell's law is that the index refraction of material 1 times the sine of the angle in material 1 equals the index refraction in material 2 times the sine of the angle in material 2. And so on this side, we're going to do everything about the air that the laser was in before it hit the D-shaped piece. And here, we're going to go ahead and do everything about the plexiglass. So angle of, the index refraction of air, we can assume that that's 1. And then this is going to be the sine of the angle of incidence. And over here, we have the unknown index refraction of plexiglass times the sine of the angle of refraction. So if we wanted to find the index of refraction for plexiglass, we would simply take the sine of theta I divided by the sine of theta R. Now, I'm going to have you do this in a slightly different way. I'm going to have you do this by making a graph. By taking this statement right here, which I will rewrite again as sine theta I equals n times sine theta R. I'm going to have you treat this as an equation in the form of y equals mx plus b. Well, there's no b, so this is gone. And that means that m represents the slope. So if we were to graph on the y-axis sine of theta I, and on the x-axis sine of theta R, then the slope of that line would be the index refraction. So that's exactly what you're going to do. Sine of theta R from your table will be graphed here, and sine of theta I will be graphed here. You'll get some data points. You'll form a best fit line with a ruler, and you'll find the slope of that best fit line, and that will be the index refraction of plexiglass. It's a fairly simple lab, but it takes a little bit of patience to get all your data down. And then, of course, it's time to answer some questions. This will not be a formal lab. This will be our traditional informal lab, and I will hand you the paper on lab day. I haven't decided when that's going to be. All right, enjoyed talking to you. See you later.